let's try this again. We want to start recording. Okay. And we're going to screen share our whiteboard application, open board. So today we're going to talk about what's called a noble gas configuration. So whenever we're talking about noble gas configurations, first off, we need to know what a noble gas is. Noble gases are elements in group 18. So this is group 18 on the periodic table. So they are called noble gases because they are inert, meaning they don't react or don't like reacting. It's highly unlikely. So that being said, we need to understand why they don't react. And to do that, we have to look at electron configurations of our noble gases. So in particular, whenever we're talking about noble gases, we're going to reference a term called a valence shell, which is our outermost shell of electrons. It refers to both the S and P shell. So it refers to our S and P orbitals. Along with that, we need to know what our noble gas electron configurations are. So with that being said, let's take a look at a couple noble gas configurations. So our first one we're going to look at is helium. Helium is element number 2. Helium is an exception to the rule. Because traditionally noble gases follow what's called the octet rule, which we'll get into in just a minute. Helium does not follow the octet rule. So we know helium has 2 electrons, which means both electrons are going to go in my 1s shell. And we know our 1s shell, if we look at our line diagram, is going to be a full shell with an up arrow representing an electron with the upspin, and a down arrow with which represents an electron with downspin. So helium is part of the noble gases, but it doesn't match the octet rule. Now, you might be saying, octet rule, we haven't talked about this before, which is true, we have it. So the octet rule basically says a valence shell is full when it has 8 electrons. So we have 8 electrons in our valence shell. Now, just as a reminder, this is only referring to our S and P orbitals, or S and P orbital shells, which we know our S orbital shell holds 2 electrons and our P holds 6, 2 plus 6 giving us 8. So looking at our next noble gas, which is neon. So we know neon is element number 10, which means I have 10 electrons. So looking at our orbital notation, we have 1s2, then we have 2s2, and then 2p6, which should account for our 10 electrons, because 2 plus 2 is 4, 4 plus 6 is 10. So notice that also our electron, or our valence shell, corresponds to our energy level. So our valence shell corresponds to our energy level. And what I mean by that is, if we just take the ones that are energy level 2, we have 2 plus 6, which gives us 8. So looking at our next example, I believe is argon. So argon should be element number 18. So we have 1s2, 2s2, 2p6. That's going to be 10 electrons, which means I have 8 left. Which is going to give me 3s2 and then 3p6 to count for my final 8. So that being said, if we look at just our line diagram for our 3s2 and our 3p6, because you guys should know how to do the line diagram for everything up to 2p6 at this point, and you should be able to do 3s2 and 3p6 actually, but we're just looking at 3s2 and 3p6 because it's what we're concerned about right now for our valence shell. So we have our 3s up, down, so we have a full 3s orbital. And then our 3p shell has 3 orbitals. Once again, up, up, up. There's 3, down, down, down. Gives us 6. So notice I have a full shell right here. So with that being said, we have this concept of a noble gas configuration. So noble gas electron configuration. And what this does is it's a way to look at only the outer electrons, because those are the electrons that are going to affect the chemical properties of whatever element we're looking at. So what this actually says is we're going to take, let's look at an example. We're going to take let's go with aluminum, which we know is element number 13. So instead of having to write out the big long electron configuration of 1s2, 2s2, 2p6, we know aluminum gas 3s2 and then 3p1. So instead of having to write out this whole chunk of electron configurations or orbital notation, instead we know that this orbital notation that we have highlighted in red is actually the orbital notation for neon, which has 10 electrons. 1s2, there's 2 electrons. 2s2, that puts us to 4 electrons. 2p6 gives us 6 plus 4, gives me 10 electrons. So we know neon equals this. So what I want to do is I'm going to take the noble gas before whatever element I'm trying to do the electron configuration of. And basically, I'm going to tell you that we know that aluminum has this noble gas configuration plus this. So dropping down here, I'm going to write this in blue. We have aluminum, which once again is 13. In brackets, I'm going to say this has the configuration of neon. And then it also has the configuration of 3s2, 3p1. So mind you, so the neon in brackets and the 1s2, 2s2, 2p6 are the same thing. All I'm doing is I'm telling you this in a shorter form so I don't have to write out that whole configuration. And this is especially notable whenever we get to larger elements. So if we're looking at elements above like 36, because then we're having to write out a ton of orbital notation. And what's the point whenever I can tell you it has the same orbital notation as element number 36? Can't think of it right now. And plus whatever. So this is a practical way to save time. So that being said, we'll look at one more example. Let's look at iron. So Fe, which is element number 26. So I have 26 electrons. So we could do it the hard way, write everything out. 1s2, 2s2, 2p6. So there's 10 electrons gone. We're down to 16. 3s2, 3p6. There's another 8, so we're down to 8. Then we have 4s2, 3d10. Or sorry, not 3d10. It's going to be 3d6 because I have 6 electrons remaining after my 4s2. Now, you might be saying, why are we not taking into account this 3d? It's just how we look at the octet rule from an electron configuration, because our 3d is so close to our next energy level that we're not concerned with those electrons whenever we're talking about our octet rule or noble gas configuration. So the noble gas before iron would be element number 18, which we know is argon. So we're going to rewrite our orbital notation as noble gas configuration. So I'm going to have AR in brackets. And then from there, we know that AR consists of up through 3p6. So I just have to continue with my 4s2 onward. So we have 4s2 and 3d6. So hopefully that makes sense to you guys. There's going to be some practice problems related to this posted on Schoology today. If you guys have any questions, feel free to message me on Schoology. All right, guys. Thank you. Turn off the video.